My name is Maxim. Currently, I'm presenting at ICLR 2026 in Brazil. So my work is about zero-shot adaptation of behavior foundational models to unseen dynamics. So the main problem we're trying to solve is how to learn a proper forward-backward representations from offline data that comes from cross-embodiment setting. So take, for example, this problem. We have data coming from this layout. As you can see, it has different walls positions. And you also have another layout. You see the walls are in different positions that are distinct from the first one. So then you collect an offline data set from both of those layouts, and you learn a behavior foundation model, like anything. You can learn forward-backward representations, or you can take another data based on another ideas like HILP or Laplacian. So, but the problem, unifying problem, is that when you're trying to extract the optimal policies from those approaches, their policies are interfere. So as you can see here, they overlap. And basically, the model is unsure about its future. It basically averages out all possible futures that are possible. So one possible simplest approach is just to learn a context representation that tries to distinguish between different layouts. So you take transformer, learn it in supervised fashion, and you get the embedding vector that corresponds to all information required to understand that this is exactly this layout and this is exactly this layout. So, of course, in practice, this is just an intuitive example. Of course, in practice, we have much broader data, for example, from robotics or some other environments. So, when you condition pre-trained behavior foundation model on this context vector, you see that the policies try to disentangle. And in practice, this corresponds to this increase in our results, which corresponds, we call it belief forward-backward. However, if you investigate further the policy space, it looks like this. And as you can see, it is very unstructured. So here, on this picture, the different colors correspond to different dynamics, different transition functions. And points corresponding to the same color correspond to different possible policies for this particular layout. For example, this one or this one. So when you extract policy, you see that there are a lot of overlaps. So the policies are still unoptimal. So the next possible idea is to somehow introduce novel prior, somehow introduce prior on the space of all policies. And basically what we did is to orthogonalize the n-dimensional hypersphere. So you take the embedding from transformer, and this corresponds to this direction. And the goal is to align all possible policies for this direction, for this particular transition dynamics, with this direction. So then you have another vector for which corresponds to another transition function, and the goal is to maximally push them apart, maximally make them orthogonal, which will be ideal. So you have this direction, you have this direction, and you make same for other directions. So as you can see, all policies that are possible for this particular layout are nicely clustered. And one benefit that you have is that you can vary the spread of those policies. So some policies are better than others, and you can vary how nicely they are clustered. So in practice, the goal is to make the optimal covering of the sphere. So we will have a lot of different clusters that correspond to different environment dynamics on the sphere. But if the training was sufficient and the everything converged, then we would have that the for backward representations dedicate some empty space on the sphere, and this empty space will correspond to novel dynamics. So at test time, when the model encounters something new, some unusual environment dynamics, or completely different, it will generalize to to this setting because it has this prior alignment with the empty space. So yeah, and for the results, you can see that our second approach, rotation FB, works much better than all previous baselines. Yeah, that's it.